2 Lab 3 circuits. So the purpose of this lab was to predict the behavior of circuits when they have resistors that are in parallel, series, and then also use multimeters to measure actual values and compare it to what we predict and with equations. A little preview of the results is on the top line. There is all of the different resistor values that were calculated. The 10 ohm battery took 10 seconds to discharge, the 20 ohm battery took 18 seconds to discharge, and the values for current and voltage by the online model match those found from formulas. The fundamental principles that we use in order to find these things and to calculate what we're doing is Kirchhoff's circuits laws, which namely say that for a node, all the current coming in has to be equal to the current coming out. And the loop rule that if a current is in a loop, the total change in voltage for one full loop is going to be 0. For steady state circuits, they're going to be equilibrium. And for Ohm's law, voltage equals current times resistance. And back with the loop rule, you can rearrange loops so that the battery is equal to the voltage of the capacitor plus voltage resistance. So for the first model that we do, all the models, the system is the circuit and the surroundings is pretty much everything else. The first circuit that we do is 2 1.5 volt batteries, 2 resistors, and 2 ammeters. So we predicted, but using the node rule, that current 1 is going to be equal to current 2 by the node rule, and so that resistor equilibrium is going to be 147. The equivalent resistor equals 147, and with Ohm's law, the current is 0.02 amps. So we actually found also 0.02 amps. Like I said earlier, the predictions match the actual values. And when we used the voltmeter, it read 3 volts, and the top ammeter read 0 for this current because there's an open circuit. When I found the different points of the change in voltage for each of the different points that are shown to the right, for B minus A I found 3, for D minus C I found negative 0.96, and for F minus C I found negative 0.204, and then the rest of them were 0. And overall, for the round trip, it ends up being 0 because of the loop rule. For Ohm's law, I also found the resistance of the wire, ammeter, and ohm resistor. I don't know why I said it like that. I found those things for the next part of the experiment, and I ended up getting that the 47 and 100 resistors were 48 and 102 respectively, and the wire and ammeter were 0 for resistance. Then when we did the part of the lab that was the RC circuits, it was bulb and capacitor in series with 10 ohm bulb, 20 ohm bulb, 9.0 volt battery and capacitor. When connecting everything, the bulb gets brighter and then dims, so it's charging. After discharging, the bulb gets brighter and then dims again, and that's discharging. The time to discharge the battery can be seen here. And then when taking the different points that we saw earlier and creating the graph, the theoretical resistance versus capacitance was 6 seconds, and then the actual resistance using this graph right here ended up being 6 seconds as well, which was found by doing negative 1 over the slope. So in conclusion, there may have been some delay in starting the stopwatch and some rounding errors that kind of made the times not as quite precise as they could have been. If we were doing this in real lab, because of resistance of the real ammeter, the current would be lower than we actually calculated or we found here. And if we were doing this with a battery to charge a real capacitor, then the capacitor would be charged immediately in the predicted model because there's no resistance in the current, but in real life, wires do actually have resistance, so this prediction would be not quite accurate. Thank you for watching.